everyone, I'm Chen here. I'm going to do a presentation about the recent work we've been doing, which is to use instrumented column testing and modeling of salt uptake from compacted bauxite residue into a cover. So the bauxite residue is the waste after minerals, particularly aluminium oxide, is extracted from the ore. This takes 99% of the entire ore, which is a significant amount, and they need to be stored properly and safely because caustic soda is involved during the mineral extraction process, which makes the tailings, the bauxite residue, high in alkalinity. Later on, it is found that a mixing of seawater with the bauxite residue is able to reduce the pH down to 8 to 9.5. But then the question is, the salinity increased significantly, which makes the bauxite residue not able to vegetate on top. So once the mine closes, it needs to be rehabilitated to allow vegetation live on top. That means a cover needs to be designed on top, allows vegetation grow. But then the question is that what is the best thickness of the cover? It has to be thick enough to prevent salt water coming from tailings up to the surface, but it also needs to be thin enough to make it cheaper. So this study is to look at what is the best thickness that is effectively prevent salt uptake and yet able to be vegetated. So here is the general procedure for tailings storage facility operation. The tailings are always coming to the storage facility through conduits. It's 25% of slurry, a lot of water. After a period of time, usually 7 to 14 days, evaporation taking place and that takes water away with solid remain. The surface becomes somehow condensed because the tailing material is relatively fine. And to be able to allow evaporation, Enferol is used to open those closed surface to allow the underneath wet tailings coming back up again. Evaporation could still keep going. So after repeated enferoling, the surface tailings becomes even drier so that dozers is able to maneuver on top. So the dozers is able to further open up the dried surface and eventually make the surface condition relatively dry. Then the process repeats. So by doing this, the permeability for the bauxite residue is able to reach down to 1 power 10 negative 19 meters square, which is 5 order of magnitude less as compared to clay, which is very, very impermeable. Now, we need to give a better design for the cover. So we decided to use an instrumented column because the column is able to do everywhere. We can't put a column right in the middle. If we put an instrument directly in this area, the vehicles is not able to move around, so it has to be a dedicated place. But so far, we managed to make instrumented columns. So once we're talking about instrumented column, the first part is instrument, and the second part is the column. We've been using quite a few soil sensors to work in tailings, but turns out the general story is most of those sensors are designed for agriculture purposes, not really for tailings. So some of the interesting thing would happen, say, because of the hypersalinity, sensors like TDR will not be working there at all. You just get some scattered results. Also, that the salinity variation in tailings is relatively high. The dielectrical permittivity method, which is usually to measure the moisture content, is not only a function of moisture content, but also salinity. So you need to recalibrate the sensor. And the other interesting thing is that some different companies come with different dart loggers. They only speak to their own dart logger. So at the end of the day, if there are 5 different types of sensors involved, we got a very clumsy system. And lastly, if we eventually find out a generic dart logger that is able to hook up to 50 sensors, the result would be different as compared to only hook up 1 sensor to the dart logger because of the zero shift. So all those questions, we decided to design some of the instrument our own or use some of the on the market sensors that work friendly to the open source field. And then we got our own dielectrical moisture sensor, piezometer, dielectrical suction sensors, thermal suction sensor, oxygen concentration, humidity-based salinity sensor, and inclinometer. So most of them has been used in this project, and all those sensors is able to hook up to one dart logger. So this dart logger powers individual sensor, do the measurements, and then send the data directly online in the web. And it's solar powered, connected to web by 3G, and there's no zero shift. So we've been quite happy with it so far. So again, sensor needs to be calibrated, and every tailings behaves very differently. So the calibration is done by a desiccation process. So the tailings with no amount of water is putting into the basin, and the basin sits on top of a scale to measure the weight loss, which can back calculate the moisture content. If the soil water retention curve is known, we can calculate the suction. Evaporation is enhanced by the fan. The thickness of the tailing is relatively thin to allow the moisture distribution uniform across the depth. And this is the picture after the tailings is being deposited. Then evaporation can start it. So here is the result. So evaporation first start off increasing slightly, and that could be potentially because the early forming of the crack, which increased the surface area, and later on increase again, which is induced by the deepening of the crack, which allows the moisture at the very bottom to be able to evaporate it. And in the end, you will see a lot of salt precipitated on top. During the whole process, the volumetric water content decreases almost monotonically, and the suction increases monotonically as well, which is well captured by the moisture and suction sensors. Now, if we move to the compacted tailings, what you will see is that there is literally no cracking formation at all, and the evaporation decreases almost monotonically, because the evaporation is not only decreased by the desaturation, but also the increase of the salt. And later on, there's a small increase of the evaporation, and this small increase is simply because we remove the cracks on top, and evaporation not need to bypass the cracks. Moisture going down, suction going up, and then the humidity going down. So the humidity is another way to measure salinity, which we've been developed recently. Now we've got all the sensors well calibrated, and then it's the time for us to do the columns. So the column we designed to be 1.2 meters, 6 millimeters per section. There are two sections. The reason we do two sections is to allow maneuvering at the bottom layer. You wouldn't be able to compact the tailings if it's 1.2 meters all the way. There are 14 sensor sockets. So the sensor installed is moisture, suction, salinity, phreatic surface pressure, piezometric pressure, and it also mount a weather station to measure weather conditions next to the columns. So this is the setup. Underneath is compacted red mud, and then on top of that we've got cover material. And this is the column immediately before it's being started. That's what it looks like from the front and back. The enclosure here is to prevent air from tipping the columns because the wind on the roof is very high. Then this is the result, almost 1 year. So rainfall is not much during the dry seasons. Actually last year there's literally almost no rain, and it was very intense during the wet seasons. And if you look at the evaporation, the brown color is the potential rate, which is in general very high, but the actual rate is only taking place when there is a rainfall event. And roughly 2 weeks or even 1 week, the actual evaporation almost stopped because of the surface is very, very dry. And at the same time, we look at the temperature. The top temperature fluctuates quite heavily, as shown by the brown color, whereas the bottom fluctuates slightly. If we look at the moisture, I think the best way to look at the moisture is at this point, as this. So the fluctuation is particularly taking place at the cover material, not much so in the red mud tailings, which means that the atmospheric recycle of the water is taking place intensively in cover, and red mud just sitting behind doing nothing. And this is also proved by the electrical conductivity sensor. So 2 of them installed, one on the surface and one at the bottom. Even there, the electrical conductivity is almost like fresh, which means literally no red mud tailings has got water moving upward. The last picture here is basically the mass balance. So we are able to calculate the mass balance by integrating the moisture sensor result We also can integrate the mass balance by looking at the cumulative rainfall and evaporation. And two methods match very well. This actually indicates that every single droplet during this 1 year is well accounted for during the experiment. Now, if we look at the physical process, what really happens for this column experiment, we know that the column's got saline water, which is subjected to weather condition, and because of that, water table goes down, and possibly salt precipitation will taking place on the surface. And to simulate that, water balance needs to be considered. So that needs to consider vapor flow and liquid water flow. Evaporation needs to be accounted for as well. Solute transport and precipitation needs to be added. And the heat equations need to be added to see the heat exchange due to the temperature differences and the heat further input, which is actually based on the surface energy balance equation, and then the heat transport down to the bottom. If it's a column, actually there is a heat dissipation from the side. So this scenario here tells a simulation result if the salt is inside the cover. So initially it was fully saturated, but because of the desaturation, the surface saturation becomes smaller. Evaporation decreases almost monotonically, but at some stage you will see salt precipitation on top. But the salt precipitation later on stopped, whereas the later salt precipitation taking place inside the soil, which reduces the porosity. And at the last stage, evaporation is induced by liquid water, which is shown on the red line, moving up and then convert into the vapor phase and eventually evaporated further to the atmosphere. So that actually means the surface is relatively dry. So to summarize the result, so the stage 1, when the saturation on the surface is relatively wet, so the liquid water flow is the primary driver for water moving upwards. And the solutes start off accumulating, but this accumulation does not induce any salt precipitation because the concentration has yet reached the solubility limit. And decrease of the evaporation rate, low porosity change, and the hydraulic connection to the surface still maintains. No salt precipitation on the surface. This is stage 1. Okay, now stage 2. Dewatering, but the surface is still wet. Salinity reached solubility limit, and salt precipitation on the surface. And evaporation further goes down. And no change of porosity due to salt precipitation. The third stage is that dry soil layer forms and very, very low evaporation rate, vapor transport through the dry soil layer, and the dry-wet interface decreases, and high salinity in the dry soil layer, and then very low evaporation rate. So that's basically the situation when the cover is saline, and that's bad. That means no vegetation is able to move there. Then what will happen if we just put the red mud tailings directly on top? Remember that the hydraulic conductivity for the red mud tailings is very, very small. And because of that, you will see even the surface is relatively wet, there is no liquid water flow as indicated by the red line, whereas all the evaporation taking place on the red mud tailings is driven by the vapor flow. And that decreases relatively quickly, but this is not really the case for our column testing. The final one is actually the cover material overlying the red mud tailings. You will see that desaturation does take place in the cover material. Red mud, not much. And the upward flow is relatively small simply because the permeability in the red mud tailings is relatively small. Evaporation still going down monotonically, but there is literally no salt precipitation taking place because all the salt source is in the red mud tailings, not much in the general cover material. So in this case, this setup is relatively fine so far. And if we've got the rainfall, the fresh water will further press the saline water down and eventually prevent the salt further uptake to the cover material, allow vegetation growth. So this is relatively fine setup. So as conclusions, instrumented column is able to use to look at the depths of the unsaturated tailings, the time for local weather to dry sufficiently the surface, and then the salt uptake. All the process that needs to be considered are the moisture change, suction salinity, water level, and even the settlements. We need to look at the problem for 1 year to allow the repeated wetting and drying processes. And the idealized cover design is able to provide a capillary break, minimize the settlement, and lastly is that the depth needs to sink enough to accommodate the root zone. Lastly, permeability of the red mud also help to reduce the salt transport upward. That's all my presentation. Thank you very much.